Welcome. I just wanted to do a few housekeeping things. I have one question about how many people here know or have heard of Neil Shubin? Neil Shubin, heard that name? Okay. He's an anatomy professor at the University of Chicago, a science writer. He found an amazing, awesome fossil you may have heard about. And you know his fossil more than him. Tiktaalik? Anyone know of Tiktaalik? Yeah, okay. He found that up in Ellesmere Island, way up in Canada, one of the few places. It was very interesting predictive science stuff. He predicted where he should look for a fossil that would be at a certain age. And the age he was very interested in is when fish were developing, their fins were developing into limbs. So he knew that this would be about 370 million years ago. He did actually a lot of oil and gas explorers know where the ages of the rocks are and what they can look for because they know where they want to dig for, mine for oil and so on. And so he found three places. One is in the Devonian, this is all the Devonian period, the side cuts in Pennsylvania, along the highways in Pennsylvania. Not a real pleasant place to dig for fossils with 18-wheelers zooming, 14 feet away from you or something like that. Others in Greenland, and that had been pretty well looked over, and it's covered with ice a lot of the time and so on. And the third was up in Ellesmere Island, way up in the north of Canada, close to the Arctic Circle. And he was able to go and find these exposed rocks of a certain proper age and look, and after, I think, about 5 years of searching in a short window of time from all his other responsibilities, they could go for about 2 weeks at a time, camp out on this stretch of cold, barren rock, and look, and it had been a sedimentary river flow there and so on. They found Tiktaalik, which was the creature they were looking for, in which the limbs, the fins were developing into limbs. It was actually a kind of a fish that could do push-ups, he described it. Okay. And, as there's a whole story about that. I've actually talked about Your Inner Fish here a couple times. He did a show on that was on PBS a little bit, and 3 segments of that. And anyways, I just wanted to see if I'd like to revisit that again, because maybe you see it kind of gets me inspired. So I wanted to see if that was something that was of interest to people coming up. Okay. So his writings describe evolutionary similarities, really, between us and all other creatures, which in one way you can intellectually say we know we all came from a common ancestor, but this guy looks for the commonalities, and we've talked about some of them. The pharyngeal nerve in giraffes and all mammals that go all the way from an intervention in, I think, the third cervix. No, it isn't. One of the third thoracic intersection where the nerve comes out, and it goes all the way down, curves under the aorta coming out of the heart, goes all the way up in all mammals, right? Once we develop necks, this nerve has to get longer and longer. It's such that it actually travels a net distance of about 6 inches in a giraffe, but it actually is 14 feet long. You go all the way down the neck and then back up again. Right? And that's something that is described as a symbol of how we are evolved and not just created. Right? So anyways, I just wanted to see if I was going on a tack that people had been comfortable hearing with about, or if you had heard that and remember that before. What's that? It had a neck. Yes. Yeah. Tiktaalik. All right. The calendar for the year coming up. Scott's taking today because he's going to be going off to the West Coast for the holidays, and I'll be talking in 2 weeks. So then the next one will be January 5th. And I don't think there's any problem with January 5th for people. If people plan on being here January 5th, it should be fine. Sometimes when it's really close, sometimes the first Sunday is January 1st. And then I maybe go for the 3rd and the 5th Sundays then, because people are recuperating or watching parades or whatever goes on. So we'll kind of be on the regular schedule. All right. Well, I want to welcome science lovers. We have young science lovers too. Josh, is that right?
Yep.
Yep, okay. And you know how I try to remind us all about how much this UU community works in concert with what I somewhat superciliously consider to be our Science Sunday goals. To look at this wonderful world of ours with interest, love, and yes, awe. Well, the theme of this whole church, this whole month, is awe. And I dig that. That's great. If you need more awe in your diet, and I'm talking about, maybe like Avoflavin, AW12, Aucon, and even that kind of healthy, colorful esterol, you've come to the right place. You're going to get more than your minimum daily requirements in a minute with Scott, as we talk about awesome things. But I welcome you to the other side of the building at 10:30. I think a wonderful way to start this month, in whatever means you consider to add more awe, vitamins, to your diet, is to hear maybe Reverend Mike Walker's sermon today about increasing our intake of awe into our diet. There's an awesome tidbit I wanted to share with you too. Coming up, the Geminids, increasing yearly in magnitude and awesomeness because of the gravitational pull of Jupiter, are going to make what is billed as a spectacular show, peaking in about 2 weeks. So just the night before the next Science Sunday, in the eastern sky in the early morning. 2 is the best time to see it, 2 in the morning, but they'll start about 9, 10 at night or something like that. If you look into the eastern sky, can you find Orion? Everyone can find Orion with the belt, okay? If you look at Orion, and Scott's more the astronomer than I, but a little bit further to the left is the kind of flat down laying Gemini, the twins, right? And you can look over and see some stars that look like 2 people laying, if you have a great, awesome imagination. And they'll be emanating, coming out. What's the word for how? Radiating from the middle of Gemini, okay? So I highly recommend taking a look at the Geminids that will be coming up in about 2 weeks. Okay. You have anything more you want to say about that? Okay. So, other than that, we're ready for some awesome talk about origins, and I'm looking forward to the discussion. So, thank you.
Scott?
Yeah.
Before you get started, I saw this strange yellow orb in the sky this morning. Is that a portent of something?
Well, I hope it's a harbinger of things to come, but I doubt it. Right. So, welcome everyone. I know some of you are here from Chicago Science Field trips, and others of you are regular attendees that have known about us for years. People who are here for the first time, I certainly want to welcome you. We have a lot of science-centric topics that we cover here. And I started off about a month ago talking about origins. Mike had suggested that those of us who recognize a lot of problems with mythology, including contemporary religious mythology, might be well served by having an origin story that we can all appeal to answer our own questions or the questions that others may raise about how did we get to be here? Where did all of this come from? So that's what I'm hoping to talk about today, continuing where we started last month. So I'm going to go quickly through a couple of these slides that I also already talked about. This is kind of a flow chart describing possible approaches to mythology. And again, I'm not going to go through these in any detail. Talk a little bit about the cosmological nugget, this idea that our universe started off as a tiny point of matter and mostly energy. and talked a little bit about cosmic inflation last time. The inflationary field that permeated the early cosmos and caused it to expand by something like 26 orders of magnitude in a fraction of a second. And then that inflate at the very end of that inflationary epoch, that's when what we consider the Big Bang, that's when it commenced. And the universe transitioned from a very cold vacuum, because when things expand, generally they cool off. Well, if you expand something by 26 orders of magnitude, the universe at the beginning of what we call the Big Bang was actually a very cold place. And then the inflationary field, I'll talk a little bit more about that in a minute. The inflationary field had a lot of potential energy that was dumped into creating particles, including particles of light and particles of matter. And I'll talk more about that in just a moment. And then the Earth was formed, the Earth and the Sun was formed somewhere around here. And later on, I doubt that I'll get to it today, but I may. We'll talk a little bit about the Earth and the composition of Earth and how some of the structures of Earth's crust and mantle and basaltic underlying rocks and whatnot, how those came to be. And so, one of the ideas of the inflationary theory is that it predicts that there will be these exotic particles, one of which is called a magnetic monopole. And many scientists have spent something like the past 50 years or 40 years looking for these magnetic monopoles to be clear evidence that the inflationary epoch preceded the Big Bang. Well, all of those searches have come up empty. So what does a good scientist do when data does not support their theory? They invent a new theory, right? So, several theoretical physicists and cosmologists have put forward this idea that one of the reasons our universe is lacking some of these exotic particles that we might otherwise expect is because inflation, this moment when the little bubble of space-time and potential that is locked up in this inflationary field, that little nugget, when it started to expand, is nothing special. It's an extension of what's called the Copernican principle, right? Copernicus kicked us off of a pedestal. We are no longer at the center of the universe after Copernicus. We were never at the center of the universe, but a lot of people thought so. Some still do. But, you know, this idea that the sun went around the Earth, that's no longer true. So the Earth is not the center of our solar system. Well, it's not the center of our galaxy. It's not the center of the universe in any way, shape, or form. Well, this idea that there's nothing inherently special about our circumstance or our position in the universe, if you extend that logical concept even further, you can conclude that the inflationary epoch that gave rise to all the matter and energy in our universe was also nothing special. And it's quite plausible, although we cannot ever conceivably gain evidence to support it, it is plausible, it derives from what we have been able to prove about the laws of physics. It's quite plausible to say that these little bubbles of inflationary space happen all the time in other kinds of bubble universes that are all sort of daughter universes from what I would call and have called a motherverse. So a motherverse has certain potentials. One of the potentials that it has is the potential to create bubbles of space-time that inflate, that have tremendously strong inflationary potential energy that can turn into mass and energy. So this has led to the idea of what's called eternal inflation, that our universe is nothing special, even though it began 13.82 billion years ago. There's nothing special about our universe except that we all love it, right? So there may be other inflationary bubble universes that have been churning and frothing since time immemorial. In fact, infinitely far in the past and infinitely far in the future. So I want to talk a little bit about how did matter come to be, right? people talk about the Big Bang and then how that's the creation of all the matter that we see. But how did that really happen? Well, I hope that you will, after this, understand a little more about how that could be possible. So, according to modern theories of physics, every fundamental particle is associated with a consistent field that spans the universe. There is one electron field. There is one electromagnetic field. Now, that electromagnetic field obviously has bumps and ripples in it. It changes character from place to place, but it is a uniform field throughout the universe. Same thing with an electron field. Right? There are other fields for other fundamental particles that I'm not going to talk a lot about today, such as quarks. Quarks comprise neutrons and protons. Neutrons and protons are comprised of quarks. And there are quark fields, right? And then there's this something called the newly discovered Higgs particle, which is a manifestation of the Higgs field. Well, in the early Big Bang, just before the inflationary epoch, scientists have reasonably postulated that all the particles of nature had zero mass. Electrons and photons and other exotic things called W bosons and whatnot. All of these particles of nature were fundamentally massless until the Higgs field decoupled from some of the other fields of nature. And once that decoupling happened, they could interact, and it's the Higgs field that gives other particles their mass. Okay, everybody understand that? Right. Why is that important? That's important because, like every other particle and field, the Higgs field can create Higgs particles. And the Higgs particle was discovered, what was it, Mike, 2016? 2016, and it was announced on July the 4th. So, one of the properties of space-time during the early universe was something called this inflationary field. Now, like every other field, it should have an associated particle. It should be something that has been named an inflaton. An exciting original name, the inflaton.
I ate a lot of them on Thanksgiving, I think.
Okay, good, yes. Some scientists have speculated that perhaps the Higgs particle and the Higgs field are synonymous with the inflationary field. So the Higgs would be the inflaton. That may or may not be true, but certainly there was some kind of particle that was the manifestation of the Higgs field. The inflationary field, and we call that the inflaton. Well, the Higgs particle has a mass about 125 times the mass of a proton or a neutron. It was a very big, heavy particle, which is one of the reasons it took a long time to find it. But like other massive particles that are heavier than protons and neutrons, these kinds of heavy particles can decay via the forces of nature, typically the weak force of nature. You know about gravity, you know about electromagnetism. There are two other forces. They're called the strong and then the weak nuclear force. One of the things the weak nuclear force does is it allows one kind of particle to turn into another kind of particle and emit a little energy in the process. All right? So via a weak interaction, the inflaton could create protons and electrons. Now the protons were generated about 0.0001 seconds after the commencement of what's called the hot Big Bang. So inflation, expanded space, that came to a crashing halt, and all the energy associated with that was dumped into creating these inflatons, and these inflatons quickly decayed via other nuclear processes into everyday particles that we know and love, like the proton, which is represented here in red. At that time, the universe had been heated to about 1 trillion degrees. Incredibly hot. But it was expanding extremely rapidly. Not as rapidly as it had during the inflationary epoch, but quickly enough that it was, although it was hot at this point, it was starting to cool off again. Again, expanding things cool off, okay? So the proton, which has a relative mass of 1, was created about, what is that, about a millionth of a second after the inflationary epoch ended. And then a whole 4 seconds later, electrons come into existence. Well, what happens when you collect a proton together with an electron? You get an atom of hydrogen. However, when electrons were around, it was still 6 billion degrees. And it was far too hot. These particles were bumping into each other with so much energy that protons could not hold on to their electrons. So it was just a soup of what we call plasma, charged particles that had not coalesced into individual atoms. But we can still talk about the nuclei of different atoms. A single proton is the nuclei of hydrogen. So we can talk about it being a hydrogen atom that has been stripped of its electron. We call that an ion. So a proton is a hydrogen ion. It's still hydrogen because we denote elements, the species of element, by the number of protons they have. 1 proton makes a hydrogen. Okay, so all of these things were generated by the collapse of the inflationary field. Right? And when the inflationary field collapsed and its potential energy was turned into inflaton particles, and those immediately decayed into regular things like protons and neutrons and electrons in this hot plasma soup in the early universe. And that's how matter came into existence. Right? Right. So you start with a proton. And about the same time, neutrons were generated. Neutrons were only trivially heavier than a proton. But one of the interesting things about neutrons is that left to themselves, unbound from atoms, neutrons decay. They're a little heavier than protons. And one of the rules that nature follows is that heavier things, if possible, decay into lighter things. So neutrons will decay into a proton plus an electron, plus some other thing, a neutrino, which you may have heard about. So neutrons were around. Neutrons were generated. They're about the same mass as protons, so that inflationary field ended, generated protons and neutrons. But neutrons only stick around for a short time, unless they're bound in atoms. But they were around long enough, and they were hot enough, moving fast enough, that they could slam into protons and make a thing called deuterium. A deuterium is a hydrogen atom that happens to have a neutron as well as a proton. Okay? And there were other protons around. And through processes such as this, you could get 2 protons and a neutron that's stuck together. The thing that sticks them in this case is the aforementioned strong nuclear force. Right? So the strong force grabs on the 2 protons and a neutron, and another neutron who is still around for at least a couple of minutes comes jetting by at a very high speed and joins the party, and it becomes a regular nucleus of a helium atom. Now, astrophysicists have calculated that if this were true, if this really happened in the infant universe, then we should see a certain proportion of hydrogen, which are protons, and helium, which are 2 protons and 2 neutrons. And that ratio is about 74% of all the stuff in the early universe was hydrogen, and about 24% of all this stuff was helium. And observations of the matter that is still around in the universe 13.82 billion years later confirms that this proportion of element generation was in fact accurate. So this was predicted by the theory and confirmed by observation. That's one of the hallmarks of science. Also during this time, a little bit of lithium and a little bit of beryllium were made. Now, if you know or have learned things about nuclear fusion, which is what I'm describing here, when particles come together and fuse into a new element. Nuclear fusion is what stars do all the time. Okay, well, at least while they're still producing energy. And you might reasonably ask, well, if the Big Bang was so hot and had so many protons and neutrons, helium atoms, and all this other stuff flitting around, then why didn't it produce neodymium and iron and praseodymium and cobalt and nickel and all of these other exotic elements that we see around us today? Well, remember, one of the things I said was that the universe was rapidly expanding and cooling. It didn't have enough time or enough energy to forge elements heavier than helium, lithium, and beryllium. So those are considered primordial elements. Now, since then, inside the core of stars, we have new elements being formed from primordial hydrogen. We have helium being formed in the heart of our own star, the sun. So new helium is still being generated in the universe by virtue of the mechanisms of stars, and more lithium and beryllium and all of these other elements that I mentioned, silver and whatnot. Some of the elements that you're familiar with only happen are generated when stars explode. Now, I'm not going to get much into that today, but one of the goals that I have for this series of talks is that if anybody has any questions about anything I'm talking about, we can take a tangent, we can drill into that, and if I know the answer, or if I think I know a little something of it, I'll tell you, and if I don't know, I'll tell you to go look on Wikipedia or something. But my goal is to make sure each of you understands whatever it is you're curious about that's related to what I'm covering today. So if it takes us 6 months to get through all of these topics, that's fine. So with that being said, are there any questions yet that you have in your mind before we move on? Yes?
Where do quarks come in?
So
What was the question?
Oh, where do quarks come into the picture? So before you had neutrons and protons, slightly before that, fractions of a second before that, in the early Big Bang, it was a sea of quarks. One of the weird things about quarks is that the color, let's see, the strong force of nature is associated with a particular kind of charge. It's not an electrical charge, it happens to be called a color charge. And because of the way the color charge works, it's different than the electrical charge. You know, the electrical charge has a plus and a minus. And it's really cool that we've invented a mathematics that can easily account for things that are plus and minus. And when you take these mathematical things that are positive numbers and negative numbers, and you play with them in equations, well, whatever it tells you about predicted effects is the same effect that we see whenever we have what we call a positive charge and what we call a negative charge interacting. So the mathematics does a good job of describing the way the electrical forces work by virtue of there being positive and negative numbers. The strong nuclear force requires 3 different kinds of charges. So it'd be a plus, minus, and a out and left field kind of charge. Well, rather than calling them plus, minus, and out and left field, they're called color charges, and they're denoted as red, green, and blue color charges. And in order for quarks to make a particle that can survive as an isolated entity in the universe, quarks need to come in triads of these 3 colors. You need to have a red, a green, and a blue. All right, that's a simplification a little bit. But when it's super hot and super dense, perhaps at the heart of a neutron star, and certainly in the baby infant instance of the universe, you could have a quark soup. Right? Quarks were close enough together, cheek by jowl, that for all practical purposes, they weren't isolated in space. They were always near another quark or 2 that was a neighbor. So for a fraction of a second after the hot Big Bang, right after the inflatons decay, there was in fact a quark soup that filled the universe. And that very rapidly partitioned itself into neutrons and protons.
So there was a quark field.
There is a quark field. There still is a quark field, yeah.
Yeah, Scott, you might have just really explained my question. Did the protons, the neutrons, the electrons, did they all kind of have a period where they found each other? Were there ever, at some point, where there were just free neutrons, free protons, free electrons that just never found each other and still exist due to that?
Yes and yes. So they did find each other. It has to do with temperature. So one of the things that I mentioned is that when you have a high temperature, an electron, which would otherwise orbit the negatively charged electron, which would otherwise orbit, which is another oversimplification, which would be bound to a positively charged proton to create a neutral hydrogen atom. When it's hot enough, those things bounce into each other, literally hit each other, and the electrical repulsion between one thing hitting another knocks off the electrons, and so you get this plasma kind of soup when it's really hot. Well, when it cools off, the electrons can finally buddy up with their protons. Whether that proton is a single proton in the atom of hydrogen, or if it's two protons in the nuclei of helium, or 3 in lithium, etc. So they were certainly free particles for a little while. You had these nuclear reactions happening where the electrons are just not relevant to this. This is a description of something in nuclear chemistry, which takes much more energy than regular chemistry. So we had that happening. And then once the universe cooled off, after about 300,000 years, you had what's called neutral hydrogen forming. And that was the first time that the universe became what's called transparent, because ions are really good at absorbing light. So the universe became transparent in about 380,000 years when these neutral atoms formed. Does that answer your question?
You would know better than me.
Okay.
So the fact that the universe was at one point like filled with light to the point where it wasn't really transparent, would that mean that technically if you went like somehow back in time, somehow was able to survive and like openly like live in those conditions, would you like be able to even see like your own hand like a foot away from your face in that conditions?
So
Say the question.
the question is, if you were a spy watching the Big Bang transpire, what would it look like? Would you be able, for example, to hold out your hand and see your hand? Well, a physicist would be challenged by that kind of question, because that presumes all kinds of things, like the existence of photons, a light source that goes between you and your hand to bounce off of your hand. Certainly at the time before free atoms, unbound neutral atoms existed, the universe was still very hot, and so it'd be difficult for the chemistry of your body to happen. But let's put some of those questions aside and just say, if you had some magical device that was particularly robust, would that magical device, how far would it be able to see away from itself? Would it be able to see an inch, a half an inch, 10 miles, a light year? I don't know the actual answer to your question in terms of numbers, but I know that from a purely what's called phenomenological point of view, in terms of what phenomena would you experience, the universe would be so dense and full of particles, and some of those particles would include ambient light, that you wouldn't be able to see anything any significant distance away. It'd just be this hot, it'd be like living inside of a bright, brilliant flame. Yes?
Thanks, guys.
Hi.
Does the concept of the motherverse that you brought up, does that have any kind of legitimate origin hypothesis as of yet?
Legitimate origin. It's not provable,
Right.
because we can't do experiments on things outside of our own universe for very technical reasons, right? By definition, our universe is what we can see and manipulate, and these other bubble universes would, by definition, exist outside of anything that's causally connected to our universe. So this gets into a realm of speculation, and there are physicists and philosophers that argue about whether it's science or not. Now, my personal position on it is that it is science, although I would maybe say with a small s instead of a big S, right? Because we can make predictions about the way the universe works that are plausible, even though we cannot directly observe the phenomena themselves. I'll give you an everyday kind of example of that. We can make a prediction about what happens in the core of a star, right? We can say hydrogen is fusing into helium, and helium eventually turns into carbon and whatnot, and then you get these shells, and I'll have a picture of that in a minute. You get these shells of matter in a star. But a star is far too hot for any kind of probe or drill or satellite or device to survive a plunge through the outer layers to go investigate what's happening at the core. So we have all kinds of circumstances in science, that's just one example, where we make plausible extrapolations about what must be occurring there given the laws of nature that we know. And some of those extrapolated properties, like what happens in the core of a star, have consequences that are derivative of those theories, right? For example, if carbon were not formed in the hearts of stars, there wouldn't be carbon around. But we know that there's carbon around. We can't see it, literally see it being formed, but we know that it was formed, and its formation is a plausible extrapolation of the laws of physics, and nothing is violated in the laws of physics. There's no extraordinary claim you have to make, like a little gremlin in the heart of a star grabs a proton and kisses it, and then grabs a neutron and hugs it close, right? You don't have to make any magical extrapolations. The laws of science, the laws of physics, plausibly can tell us how it is that the hearts of stars work. In a similar way, the laws of science about the way fields and forces and interactions occur in nature, mechanisms that have been well validated by the activity of particle accelerators and whatnot, those same laws of nature can make extrapolated claims about the very nature of space-time, the very nature of matter and energy. And one of those plausible extrapolations is that the Big Bang was either a unique event, in which case it would have left a unique signature in terms of some of these magnetic monopoles and whatnot, or the Big Bang was some other kind of event. So it was either unique and happened according to all the laws we know, which would have caused monopoles, or something else happened. Well, a plausible explanation, a relatively simple plausible explanation for this something else is to say it wasn't unique. There's lots of them happening. And that gets rid of the magnetic monopole problem. And it also keeps us from saying there was some special time that made our special universe, right? There's no, the logical fallacy with a special pleading, right? There's nothing special. The Copernican principle is preserved. So a lot of principles are preserved, and these ideas are consistent with the known laws of nature, but you cannot demonstrate it. You can't extract evidence from other universes to show that they exist. So it's not quite as on firm ground as what happens at the heart of a star, which is also unobservable, right? But it is still plausible, and I think plausible enough to be considered science. But that's my opinion. There are philosophers and scientists who might argue with that, niggling arguments about terminology.
Can you go over the timeline again? I think it seemed like everything was happening in nanoseconds, and then all of a sudden I heard 300,000 years. And at what point were there helium, and what point was there hydrogen?
Okay.
I think that's not clear.
All right, so remember one of the things I said is that a neutron left to its own devices will turn into a proton and an electron after about 15 minutes. Well, that's actually called its half-life. So if you have 10 neutrons flitting around in space, In 15 minutes, 5 of those will have become protons and electrons. 15 minutes later, of the 5 that remain, about 2 or 3 of them will have become protons and electrons. So that you only have a couple of neutrons remaining. So that's called the half-life of neutrons. So it's called cosmogenesis, cosmological nucleosynthesis, which is a wonderful mouthful. Cosmological nucleosynthesis. That process of creating helium from primordial protons and neutrons shut off after about 20 minutes or 30 minutes because most of the neutrons that had been generated by the collapse of the inflationary field, most of those neutrons had decayed already into protons and electrons. So there weren't neutrons available for this process to continue. So the synthesis of helium, lithium, and beryllium from protons and neutrons stopped after about half an hour, after the commencement of the hot Big Bang. Now, the 380,000 years, that's how long it took for the universe to expand and cool off enough that the ambient temperature through collisions and because of photons of light, which carry energy, the ambient temperature of the universe had become cool enough by about 380,000 years that neutral atoms could form instead of ionized atoms. And it's from about 380,000 years after the commencement of the Big Bang, the hot Big Bang, that's where we see the cosmic microwave background radiation. Because the light associated with all the heat that the universe contained at that time, that light could finally travel through the universe instead of being constantly absorbed by all these ions. So the universe became what's called transparent at that point. All right? And then the first stars formed, and the light of the first stars reionized atoms in space. But by that time, they were so spread out that the universe remained dark. Does that answer your question?
I think so, but for that 380,000 years, there was more than just plasma, or was there still what you call plasma, or just ionized particles?
Yeah, there were mostly ionized particles that were cooling off and clumping up. Cosmologists don't think that any stars were formed during that period. It just stars didn't come into existence until about 1 million years after the start of the Big Bang, when things had cooled off enough and the little clumps of matter had been able to accumulate enough material to ignite stars. John?
Where in the process did the matter-antimatter war take place?
Oh, that's a good question. I will repeat it. Where in that process did the war between matter and antimatter happen? As far as I know, the answer to that is not yet fully determined. So there's more matter in the universe than antimatter. Every time a particle, whether it's a photon or an inflaton or a Higgs particle, anytime we see one of those particles today that decays into other particles many times, they create matter and antimatter in equal abundance. All right? And the question is, if all you, let me clarify that even more. If energy, a particle of a force field, like the inflationary field or the electromagnetic field, which is a photon, anytime one of those particles, which has a neutral charge, decays into a charged particle, there must be a positive and a negative. Well, the negative or the positive, depending on the particle, always takes the form of matter versus antimatter. So in every experiment we've done where matter is generated from energy today, equal amounts of matter and antimatter are generated. There's an inherent asymmetry in nature, and that gets off into a whole other talk about symmetry theory, which is beautiful and one of my favorite topics, but I'm not going to go into it in detail today. There's an idea that derives from studying the symmetries that nature exhibits. There's a symmetry of motion. Anything that's here will behave the same as something that's over there, right? So there's a symmetry of location, there's a symmetry of motion, there's symmetries of rotation, and you can derive nearly all the fundamental laws of physics by considering the possible symmetries in the universe. There is something called a broken symmetry. It's called the charge parity symmetry, and if you add time reversal to it, don't get me started, you've got something called charge parity time reversal. And all of these symmetries are entailed in the epoch generation of matter and antimatter. Physicists are certain that there is a fundamental asymmetry, or broken symmetry, that at super high temperatures and in super specific contexts where the energies are so high that all of the different forces of nature have not frozen out into their own particular four forms that we see today: gravitation, strong and weak nuclear, and electromagnetic. Sometime back when at least a couple of those forces were united into a single mechanism, there was an asymmetry that favored the generation of matter over antimatter. Now, the specifics of why that occurred, and what temperature that occurred, and what temperature that corresponded to in the early universe, those questions are not yet, as far as I know, definitively answered. But because there's more matter than antimatter, they know they're on the right track. The details just haven't been worked out yet. But it certainly happened maybe sometime when that Higgs particle, or the inflaton, first decayed to generate matter. Sometime between protons and neutrons being generated and the inflationary field collapsing, so sometime in the first millionths of a second of the Big Bang, that decoupling, that symmetry breaking that allowed for more matter to exist, that happened. And it was such an energetic, such a tremendously hot context that no particle accelerator on Earth can conceivably reproduce those situations.
Scott,
Yeah.
can you define or describe what you mean by temperature and heat?
Yeah.
In the context that you've been using those words?
Okay. Temperature and heat. So you may recall from grade school, maybe, that the three ways, is it three ways that heat is, that temperature is conveyed from one place to another? No, I'm good. Well, actually, that'd be fine. Conduction, convection, and radiation. Remember those? Right? So heat can be a measure of any of those. Conduction is really a measure of net atomic motion, or particle motion. Oh, now I'm talking with my mouth full. So if you get a bunch of particles moving quickly, jiggling around or jetting around in straight lines, that motion, that aggregate motion, is what we measure when we measure the temperature of something, generally speaking. Right? If we stick a thermometer in a thing, it's the net motion, the fast jiggling, wiggling, and spinning and jetting of different particles. Right? There's different ways. Right? You can spin. You can store energy as spinning. You can store energy as moving. Right? And you can store energy as vibrating. If you've got a molecule with more than one atom, it can vibrate. So there's different mechanisms that a molecule can use to store energy. Well, if you've only got single particles, right, there's really no jiggling to be had. And spinning isn't really important. So the temperature of the early universe is mostly entailed in the motion of elementary particles. Also, there's radiation. So at different epochs, some of these epochs lasted fractions of a second. In the early universe, an epoch is like a phase change, like between ice and water, right? So during some phases of the early universe, there were times when there were a huge number of photons. So much of the energy of the universe would be locked up in photons. That's where the temperature comes from in that context. At other times, almost all the energy, like when the universe was just a sea of quarks, almost all the energy is locked up in quarks. And in the particles associated with the strong nuclear force called gluons. So almost all the energy in the universe was in the motion of quarks and gluons. So temperature is a measure of generally either the intensity of radiation or the speed of particles. Well, the speed or temperature of particles is also something really important to consider when talking about particles colliding and potentially either sticking together or bouncing off of one another. Different effects happen at different temperatures, which means different effects happen at different speeds of those particles. If you get protons moving fast enough, even though they have electrical repulsion between them, they can get close enough that the strong nuclear force can grab on and bind them together. So temperature is very important for describing the energies. Temperature and energy are kind of synonymous terms. Temperature is an important way of describing what physical processes can happen at what energy levels. Okay? Yep.
I'm stuck at the universe versus the motherverse. And if the universe were a singular event, it would have produced particles that had not been found. Is that correct?
Mm-hmm.
But if it were not a singular event, but if it were happening often, or had happened often, wouldn't it make sense that there would be even more of those particles that would be available for finding?
Yeah, great question. So this gets into questions that I cannot answer that question in detail because I'm not a theoretical particle physicist, cosmologist, but my understanding is that if the Big Bang were a singular event, then the properties of the motherverse, if you will, if there's only one daughter of the motherverse and we're it, then that motherverse that gave rise or birth to our universe must necessarily have had a certain set of properties. And one of the ways we can recognize those properties is as the creation of these magnetic monopoles. If instead the motherverse gives rise to a litter of universes, right, instead of just one, then the motherverse has a different set of properties. And that different set of properties means that it doesn't have to create these magnetic monopoles anywhere, not in our universe, not in any other universe. So that's the best I can do to answer that question. All right, can I move on?
Scott,
Yeah.
why doesn't the electron just jump onto the proton and neutralize it at the end?
So electrons do, in fact, I had created a slide animating that. Electrons and protons sometimes join together by a mechanism of the weak nuclear force. Well, one of the properties of the weak nuclear force is that it's weak. It doesn't happen very often or very energetically. So you could, and you do have within our universe, within the hearts of stars, you do occasionally have a proton absorbing an electron. So like a little more complicated than that, and becoming a neutron. But that happens rarely enough because the weak force is such a weak force that it wasn't really relevant in the first few minutes of the Big Bang. All right? So, this is a diagram of the way hydrogen turning into helium works at the heart of stars. Even though we can't send a probe in there and measure it, we can do these kinds of experiments in particle accelerators. And we validated that this mechanism works. Now, remember I said that most of the cosmological neutrons had either been incorporated into helium or they had decayed away into protons and electrons by about half an hour after the commencement of the hot Big Bang. So there really aren't many, if any, free neutrons available in the universe, including in the hearts of stars. So what Joanne was just asking about was protons interacting with electrons. In this case, it's a positron. It's the antimatter version of an electron. A proton can emit a photon or a neutrino and a positron, and that can generate a neutron. So neutrons can be generated from protons in the hearts of stars as long as there is available energy. And it's this very complicated process since there aren't any freely floating neutrons available in the hearts of stars. This is the way stars make neutrons that get incorporated into helium nuclei. I'm not going to go through this in detail. I just want you to recognize that this is much more complicated than the kind of nucleosynthesis that happened in the first few minutes of the Big Bang.
Where could I find that?
Wikipedia.
That picture?
Yes.
Okay.
Yeah, you do a Wikipedia search for, what's that, helium nucleosynthesis, or helium fusion, I guess. Several different paths will lead you to that page that has this diagram. All right, so you've heard about fusion being the energy future of the world, right? And a lot of times when the press gets hold of these stories, they distort the science a little bit. One of the things that is sometimes, perhaps too often, said about fusion reactors that different consortiums around the world are trying to build is that a fusion reactor captures the processes and recapitulates the physics that occurs at the hearts of stars, right? So by getting a fusion reactor to happen here on Earth, we are taking a little piece of star physics and incorporating it here to liberate energy. Because when you combine two protons and or two neutrons together to make helium, that actually releases a little bit of energy. It releases more energy than it takes to smash them together in the first place. So that generates or liberates energy, which is why stars shine, right? But characterizing the fusion reactors that we're trying to build on Earth as being examples of what happens at the heart of a star is completely wrong. Instead, every fusion reactor that is being built on planet Earth, it captures the science of what happened in the first minutes of the life of the universe. Because it's taking deuterium or tritium, which is heavy hydrogen, usually extracted from what's called heavy water. It's taking deuterium and trying to add a proton to it. Or it's taking tritium and trying to add a proton to it. And those kinds of reactions happen at a lower temperature than the temperature in the hearts of stars. And it's a much simpler process. And because it happens at a lower temperature than the temperature in the hearts of stars, we can access those temperatures, we can generate those temperatures more plausibly here on Earth. So the fusion reactors you hear about and read about are not, in fact, bringing a piece of stars down to Earth. It's bringing a piece of the Big Bang down to Earth, but in a very safe and contained way. All right?
I just want to say, I'm not enabling
So
contributions major.
it's almost time for me to stop today. I can start off next time talking about the way stars work and how the first stars came into being. But I have time for a couple more questions before we adjourn for this time. All right? Good.
Here's one.
Oh, Charles.
I have a question. So inside like Fermilab, the temperature doesn't get that hot. Why doesn't everything in there melt? Like what material is it that is?
Right. Okay. So in fusion reactors and in particle accelerators, the things that are moving very fast that correspond to what we would call a high temperature, generally those motions occur in a vacuum. All right. So one of the things that Fermilab does is they evacuate a tube of essentially all the air and all the sputtering molecules that come off of the sides of the tube that they're in, and try to evacuate that so that the heat isn't conducted to the surrounding equipment. And sometimes after a collision happens in a particle accelerator, the particles that spray off of that collision, well, they're carrying that energy, they're carrying that heat, and it heats up detectors. And by microscopically understanding where in a given detector a particular hot reaction occurred, that's how we know what happened during a particle collision in a particle collider. In a fusion reactor, like I showed a moment ago, the issue is to keep that temperature contained so that it doesn't heat up the apparatus. And they do that generally with magnetic fields. Some do it with lasers as well. They sort of float atoms of tritium and hydrogen in a laser containment bubble. But you do have to contain that. Otherwise, the temperature of the reaction can transfer heat to the surrounding material, and it can cause problems. And it's one of the biggest engineering problems associated with fusion reactors. Yep.
Where does dark matter enter into the picture?
Where does dark matter enter into the picture? Somewhere in the first few minutes of the Big Bang, dark matter was very likely generated. It didn't happen at the very earliest stages of the Big Bang because cosmological evidence shows that dark matter is what's called cold. So the cosmological model of the Big Bang that is currently en vogue says that it's the cold, dark matter version of the universe that explains the universe that we see. If dark matter interacted with some of these more primordial processes in a very energetic way, that would have left a signature, pardon me, in the cosmic microwave background. So at some time during the first few minutes of the Big Bang, some process generated dark matter, but nobody even knows what dark matter is yet. So knowing how it was generated and when and at what temperatures and by what physical mechanism, those are still completely open questions. All right, that's probably a good time to wrap. We will continue this discussion in the third Sunday
in January.
And in the meantime, the Humanist group, of which I'm a board member, will have our holiday party here at the church on December 11th, 6:30. It's a potluck, and we're asking people to bring a wrapped book. If you want to participate, please bring a book to give as a white elephant gift we can exchange. What do we all love books? So that's it for today. Thank you very much.